Good evening and good morning, everyone. I'm Jinfeng Zhang, a researcher from Recon AIP. Today, I'm going to host the third TrustML Young Scientist Seminar. Before that, allow me to briefly introduce the Recon AIP to our valuable guests, Bo and Francesco. The full name of Recon AIP is the Recon Center for Advanced Intelligence Project. AIP was founded in 2016 at the Research Center for the Max AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance the AI fundamental technology and its real-world applications. AIP encourages the collaboration with various researchers and engineers in related fields. We would be grateful if you could visit us in our Nihonbashi office in Tokyo in near future. Well, next, let me introduce our valuable guests, Bo Zhao from University of Edinburgh and Francesco Cross from University of Tübingen. All right, I think Bo Zhao will give his talk first. Later on, Francesco will give his talk. Okay, Bo Zhao is a PhD student and Dr. Haiking Bailing in the School of Informatics, the University of Edinburgh. His research interests include machine learning, computer vision, especially efficient deep learning, meta learning, and continual learning. He has published papers in ICIR 21 oral, ICML 21 18, ACM GOG 18, and SIGGRAPH Asia 16, WACV 21 and 19, etc. He served as reviewers in NeurIPS, ICIR, ICML, CVPR, ICCV, ECCV, AAAI, TNLS, TMC, etc. And Francesco Cross is a PhD student in the machine learning group at the University of Tübingen, Germany. He received his bachelor in mathematics for finance and insurance, and his master degree in mathematics from the University of Torino, Italy. His research focuses on adversarial attacks in different threat models and provable robustness. All right, let's proceed to start our first talk. Hi, Bo, can you share screen?
Yeah, thanks, Jinfeng, for the invitation. So good evening and good morning. Today I will present our recent works on dataset condensation for data efficient deep learning. These works are collaborations with Konda and my supervisor Hacken. So we know to achieve the state of art, we typically need to train deep neural networks on large-scale datasets. This figure shows that the computational cost to achieve the state of art doubles every 3 months and in the deep learning area, which is significantly faster than the Moore's law that doubles every 6 years. In addition, this figure only shows the cost for training a single neural network. However, we know when we try to design like new modules or new loss functions, such hyperparameters, we probably need to train multiple networks or architectures on the single dataset. So it's extremely important to reduce the computational cost while achieving good performance. So our work is try to reduce the computational cost by reducing the training set size. Given a large dataset T, we can train a neural network set T and then test it on the real testing data. We try to condense it into a small synthetic set S, and then train the network theta S on the synthetic set S. We hope that the testing data of theta S and theta T are comparable. So the classical methods to reduce the training set size is cross-set selection. So in cross-set selection, give a large training set, we try to find some informative samples based on some heuristics. For example, here we expect that those data located at the cluster centers are more informative than the others. So we can find these cluster centers and choose them as the core set. Then we train downstream models on those selected data points. However, the core set selection methods have two main weaknesses. First, they rely on the heuristics and the greedy algorithm, which are usually short-sighted. Second, they usually need, they also relay the presence of the representative samples, which is not guaranteed. So recently, the dataset distillation is proposed. Sorry, can you see the title of this slides? Because in my screen, the title is
yes, the title right now is a related work dataset distillation.
Yeah, okay, great. Yeah, because in my screen, the title is overlapped by the by something else. Okay, no problem. Okay, yeah. So recently, work dataset distillation is proposed. So they try to learn a synthetic set instead of select some informative ones. So here there is a learnable synthetic set S. Then they use it to update a network CIS for several SDD steps, and then they evaluate the CIS on the real training data T and get the mental loss or mental classification loss LT. So they try to learn the synthetic set S by minimizing the mental loss on LT. This method have two main weaknesses. First, it involves a nested loop optimization as a mental learning method, which is difficult to optimize. Second, it needs to unroll the recursive computational graph, which is not scalable to large models or large data sets. So we propose dataset condensation with gradient matching to solve those two problems. Firstly, we try to implement a dataset condensation with parameter matching. So we expect that the models trained on the large dataset and a small synthetic set has not only similar performance but also similar solution paths in the parameter space. Therefore, we match the parameters theta t and theta s. However, such idea still have similar problems like the previous work dataset distillation. It also involves many local minima traps in the parameter space, which is very difficult to optimize. Secondly, it also needed to unroll the recursive computational graph, which is not scalable. Then we propose the dataset condensation with curriculum distribution matching, gradient matching. The motivation is that we expect the model trained on the large dataset and a small synthetic set have not only similar solution, but also similar solution paths throughout the optimization. So given the large training set T, we can train and also a model theta T. Then we can get the classification loss LT on the dataset T. We do back propagation and get the gradients with respect to the dataset T. Similarly, for the small synthetic set, learnable synthetic set, we also get the gradients with respect to the small synthetic set. And we expect that for the same theta T, the two gradients are close, similar. So we match their gradients and get the gradient matching loss. Then we can learn the synthetic set S by minimizing the matching loss. Then the theta T is updated on the synthetic set S. So the new method successfully avoided the dependence on previous model structures and in a nested loop optimization. And then it also provides dense supervision as a curriculum in the learning process. We also designed a new gradient matching loss, which works better than the traditional L2 cosine distance. So here we know that the gradients of deep neural networks are usually have diverse or special structures, and directly vectorize them is not a good idea. So we first decompose the gradients or the weights. Then we group the gradient variables connected to a specific like output neuron, as shown in the figure. Then we group these variables as a vector and calculate the cosine distance of two vectors. Then we sum all the distance between the vectors connected to each output neuron. Sum for every output neuron and also for every layer, and get the final gradient matching loss. Similarly, for convolutional layer, we also group those gradient vectors connected to each output neuron. So if you have any question, you can interrupt me and ask anytime. Then this is the training algorithm. I'll give so here for each training step, we first randomly initialize the theta 0, the model. Then we update the synthetic data and the model theta t alternatively. When we update the synthetic set, as we update class by class, we match the gradients class by class. For each class, we sample the mini batch of real data and synthetic data, and then calculate the classification loss and also the gradients. We update the synthetic set by minimizing the gradient matching loss. Then we update the theta on the synthetic set and alternatively do it. We do experiments on 4 image data sets. They are MNIST, fashion MNIST, SVHN, and C15. So the experiment includes 2 stages. In the first stage, we need to learn a condensed set of images. And in the second stage, we will evaluate the condensed images by training neural networks from scratch on those condensed images, and then evaluate on real testing data. Note that the models or the architectures used in the 2 stages can be different. We can learn on the synthetic images on one architecture and then evaluate them on another architecture. This figure shows the performance comparison to the best cross-set selection method, holding. So the horizontal axis denotes the size of condensed set, and the left y-axis denotes the absolute accuracy of the model trained on the synthetic set or the cross-set selected by holding. The right axis denotes the relative performance, which is calculated by the absolute accuracy divided by the upbound. Upbound is the performance trained on the whole data set. So this figure shows that our method always outperforms the best cross-set selection method by a large margin, and we also achieve 98.8 testing accuracy on MNIST with only 50 synthetic images per class, which is only 1% of the original data set size. We also compare to the previous work data set distillation. So in the table, we show that our 1 image per class learning performance on MNIST is can outperform data set distillation's 10 images per class performance by 5%. Our method also need like half less training time and memory cost than the previous data set distillation method. In the right figures, we compare the synthetic the images synthesized by our method and the previous work data set distillation. If we look at the MNIST images, the MNIST images synthesized by data set distillation looks like noisy. And it's hard to recognize. However, the MNIST images synthesized by our method are recognizable. And we can see the semantics and the diversity in those synthesized images. We also implement the cross-architecture generalization promise. So we train the synthetic samples on one architecture, on the architecture in each row, and then test on the architecture on each column. The results show that the condensed sets learned on convolutional neural networks have good cross-architecture performance. We also applied our method to continual learning. So in continual learning different continual learning methods usually needed to construct a memory to store some old knowledge from other tasks. So our method can replace the memory construction strategy by the dataset distillation, dataset condensation. So here we implement incremental learning from SVHN to MNIST to USPS, and we build our method on the popular continual learning method, end-to-end incremental learning, and we replace its memory strategy with our dataset condensation method. And we show in two settings, our method can always outperform their memory construction strategy. We also show that our method can be used to speed up neural architecture search by providing a cheaper proxy training set. So previously, neural architecture search needed to evaluate many architectures on the large dataset. Here we try to condense it and then use a small proxy set to evaluate every architecture and then rank them. The results show that our method significantly reduced the training cost and also achieving high performance correlation between the performance on the proxy sets and the performance on the large data set. So our method can be used to select to do new architecture search to select the and rank the architectures. In conclusion, in this paper, we propose an effective dataset condensation method with gradient matching, and we verified that these synthetic images are more data efficient and architecture generic. We also applied our method to continual learning and new architecture search and show promising results. In the next work, we propose dataset condensation with differentiable semis augmentation. So we know that the data augmentation is an important strategy to improve the data efficiency. So in dataset condensation, we can apply the data augmentation to the real data batches and synthetic data batches in both condensation phase and testing phase. However, if we just naively apply different augmentation strategies to the real and synthetic data batches in condensation, we find that the performance neither drops or have negligible gains. So the reason is that the linear synthetic images have different characteristics from the natural images, and also simply applying random augmentation to real and synthetic images can lead to averaged effects, which are difficult to learn to disentangle. So we propose the differentiable semis augmentation for dataset condensation. Here, the differentiable means that the gradients can go through the augmentation module to the synthetic set. Semis means that for each sampled real data batch and synthetic data batch in the training, we also sample the augmentation. The augmentation is parameterized with omega, a parameter omega. For example, the omega can denote the rotation degree of a rotation augmentation. Then we apply the same augmentation, the same rotation degree to every samples in the two batches, and then calculate the gradients and do gradient matching. So the benefit is that the new method exploits more information from real and synthetic images, and the sharing transformation enables the learning some prior knowledge For example, the objects are usually like horizontally on the ground. And it will be easier to learn to disentangle the augmentation from semantics by using our proposed differentiable semantics augmentation. This is a training algorithm. The algorithm is based on the previous work. So when in the step 6, when we sample the real data batch and synthetic data batch, we also sample an augmentation parameter, and then we apply the semantics augmentation to the two batches and calculate the gradients and do back propagation. We also do the experiment on the same data sets and the same settings. In this table, we show ablation study and show that the proposed semantics differentiable semantics augmentation works better than the naive augmentation strategies. In this figure, we show the comparison to the previous method. As shown in the figure, on the CIFAR-10 dataset, our method can outperform the previous state-of-the-art by 7%. And we also achieve more than 99% testing accuracy on MNIST dataset with only 1% training data. More results can be found in the papers. Similarly, we also play the incremental learning experiment and show that the synthetic images generated by the new method is more data efficient than the images generated by the previous method. Similarly, we also implemented the new architecture search experiments and show that the synthesized images can work as the proxy set to speed up the new architecture search and get a high performance correlation. We also investigated why the proposed differentiable semantic augmentation works. So here we plotted the gradient magnitude distribution about the gradients with respect to the real data batch and the synthetic data batch with or without a differentiable semantic augmentation. If we compare to the right two figures, after applying the differentiable semantic augmentation, the gradient magnitude of synthetic data batch significantly increased, and the distribution is closer to that of the real data. It means that the proposed augmentation strategies enable that the synthetic data learning more from gradient matching. This figure shows the learning procedure of so our method can learn from the random noise. We can initialize the synthetic set S with random noise or random select the real images. Our method works well with both two kinds of initialization. And when we look at the results with real image initialization, we find that the synthetic image can inherit some contents from the initialization. For example, here the car pose is consistent with the initialization, and the color is also consistent with the initialization. So in conclusion, this paper enables a learning synthetic training set that can be effectively used with data combination. We achieve better performance, around 7% improvements on CIFAR-10 and CIFAR-100. We also show promising results in continual learning and neural architecture search. The third work is the dataset connection with distribution matching. We know that the cross-hair selection is easy to implement. It has a good generalization ability. However, the weaknesses of cross-hair selection includes that they are usually short-sighted. They are based on heuristics and greedy algorithm. And they also the existence of the representative samples are not guaranteed, so they may be not able to select some representative samples. The dataset condensation methods can learn with a long-sighted objective and also synthesize non-existent samples. However, dataset condensation methods are usually expensive to optimize because it involves high-level optimization and second-order derivative. And the synthetic samples are usually biased to a specific architecture and have weaker generalization ability. So the question is that can we trade off the two? In this work, we propose a dataset condensation with distribution match to trade off the benefits of coset selection and dataset condensation. So the idea is that we embed the real data and synthetic data into embedding spaces and match their distribution in many sampled embedding spaces. So this is the training algorithm. For each training step, we randomly sample a network parameter theta. Then we sample the data batches, a real data batch and synthetic data batch and augmentation for each class. Then we calculate the mean of the data batch in the sampled embedding function with the sampled embedding function. And then we update the synthetic theta by minimizing the matching loss. So the new method is extremely simple. It doesn't have bi-level optimization or signal gradients. And it also involves fewer hyperparameters. It has better generalization ability by capturing the real data distribution. And it also so the new method can also learn different classes in parallel because the learning of each class doesn't depend on other classes, so they can be learned in parallel. Thanks to the simplification, we can apply dataset condensation to large dataset, tiny ImageNet. So in this table, we show that the new method achieves comparable performance or better performance to the state result. And we also for the first time show the results on the large dataset, tiny ImageNet. The figure shows that the new method can requires much less training cost to condense the dataset. In this figure, we show that our method can effectively learn large synthetic training set. For example, 500 images per class. Our method can continuously work better than the random selection coset method. We also verify the good generalization ability of the new method. So here we compare to the previous work. We show that when we learn the synthetic set on ConvNet and evaluate it on different architectures, our new method achieves better performance. We realize it, and we find that the synthetic images by the new method can better capture the real data distribution than in the previous methods. As I mentioned, we randomly sample the networks. However, we know that networks can be random initialized ones, can also be some pre-trained ones with different testing accuracies. Hence, we investigate whether our method can work well with different neural architecture or network distribution. So we pre-train a set of networks with different validation performance. For example, here 20 to 30% testing performance. Then we train and the synthetic set on different network distributions. We show that the performance of those synthetic sets learned on different network distributions are close or similar. However, they visually they are quite different. They have different appearances. The possible reason is that although learning on different network distributions, they all can capture the semantics. We also implement the incremental learning and show that the new method works better than the previous dataset condensation for the memory reconstruction, and also show that the new method works better in neural architectures search experiments. So in conclusion, in this paper, we propose a simple but effective dataset condensation method with distributed meshing. We also achieve the state-of-the-art performance with much lesser training cost. We also have better performance in cross-architectural generalization, continual learning, and neural architecture search. So in the future, we will explore the use of condensed images in challenging datasets like ImageNet. Thank you for listening. Any questions? Welcome. I see there is some questions.
Yes. Basically, I have two questions. I also type it on the chat box. If anybody have questions, welcome to ask. But my question is, would the condensed dataset preserve some privacy of the original dataset? SIMI is a very useful technique for publishing some proxy dataset. What do you think?
Yeah, so the condensed datasets, if we look at those images, actually it's quite hard to match those condensed images to real images. If we look at the synthesize process like this, although we initialize them from random sample once, it's hard to find the correspondence. So it can, to some extent, protect the privacy of original dataset. And recently, we also have some work about how to avoid the membership attack by using dataset condensation. So it will be a useful tool for protecting data privacy.
I see. Yeah, this basically come to my second questions. Since you are in your previous three works, you only use the accuracy, the for condensation the data set, synthesizing the data set. What the different metric, for example, like you said, you use the privacy metric. What I care about is sometimes maybe the robustness metrics. Can we use some different metric to consolidate the data set? What do you think?
Yeah. It's a good question. So our work is, the goal of our work is to learn training efficient samples. So we design such kinds of loss function about gradient matching or distributed matching. So if you want to learn with different objectives or goal, for example, you try to learn adversarial robustness. I think you can learn with different metrics so that the synthetic samples can equip with such ability. So,
I see. So yeah, basically you didn't try this. For example, you use the robustness metric to get a data set. How about the natural accuracy when you use it? For example, when you use the natural accuracy to get the data set, how about the other metric, for example, robustness? Have you ever tried this? Yeah.
No, actually we haven't. We still focus on improve the performance, the training and testing performance. Actually, so we also tested the generative adversarial network. So previously, such generative models are designed for generating real-looking or visually pleasing samples. They are not designed for improve the data efficiency. So and with such like GAN adversarial supervision, they can synthesize real-looking samples. However, they are not efficient for training. So based on this results, I think that if you you need to use a specific loss function for specific task problem or synthesize.
I see. Yes, I see. I got it. Thank you very much. Those are all my questions.
Thank you.
All right. Since no other question coming up. All right. We sincerely thank you, Dr. Zhao, to come for us to give us his wonderful talks about his research. Hopefully, when the situation is lifted, we could visit you. You could visit us in our Nihonbashi office in Tokyo in the near future. Thank you very much.
Looking forward to it. Thank you very much.
Thank you. All right. Next, we sincerely welcome our second guest, Francesco, to give us his talk. Hi, Francesco. Can you share your screen?
Yes. Hello, everybody, and thanks a lot for the invitation and for being here today. So I would like to talk a bit about adversarial robustness and how and if it is possible to have a standardized evaluation for it. In particular, we focus on image classifiers. This is based on works which I've done jointly with several co-authors, in particular Matthias Hein, my supervisor, Maxim Andriushchenko, Vikash Sevag, Eduardo Benedetti, Nicola Flammarion, Pratek Mittal, and Moon Chiang from different institutions. Okay, first, about a bit the motivation of these works and why is an adversarial robustness benchmark helpful in the first place. There are several reasons. The first is there are a lot of works appearing like almost every day about adversarial robustness, and many of them are about adversarial defenses and adversarial attacks. So, and as an example, so here is the plot from Nicolas Carlini's webpage, where he counts basically the cumulative number of papers in the topic which have appeared on arXiv, right? So, and this number is quite high already, and is growing pretty fast. So keeping track of all of them, it's not easy. So the second reason is that in general, evaluating robustness for the study examples is a difficult task, right? And it's easy to overestimate the actual robustness. So, and for example, there have been several papers like showing that, so introducing new methods, new attacks, and showing that previously proposed defenses were actually less robust than what expected. And then, like often these evaluations are done with adaptive attacks, and which means that you take a specific defense and you design a new method to break this defense, and it's not clear if the same method actually is effective on other defenses. And the problem is that this is clearly okay. The good thing is that this is effective, right? This works. But the one drawback is that this is time consuming, and in the end you have different evaluations which is not clear how comparable are. Okay, so our goal here is to have a standardized adversarial robustness benchmark. And okay, what do we need to build such a benchmark? Well, first we have a way to actually evaluate robustness in a standardized way, in the sense that we need some protocol which gives an accurate evaluation of robustness, and this works across classifiers, dataset, and threat models, so that we can use this as a minimal. Okay, I guess I will answer the question later. Okay, and we can have a minimal, but sufficiently accurate evaluation without designing new attacks. And then we still need adaptive attacks in the sense that okay, any standardized evaluation cannot be perfect, in the sense that there will always be corner cases or like unexpected behaviors for which will make this standardized evaluation partially fail. So we still need to integrate adaptive attacks in our benchmark. Then we need we at least assume we need some restrictions on the classifiers we actually consider in the benchmark. And the main reason for this is that we want to rule out some methods which make standard attacks to fail without actually improving robustness. We'll discuss this a bit later. And finally, we want to consider first threat models which are well defined and commonly used. For example, like robustness on cipher 10 with respect to infinity bounded perturbations is a super common threat model, and there is a lot of work on this. So there are also a lot of defenses to compare. So it makes sense to use this as a case for our benchmark. Okay, and now we follow these principles, and we design a robust bench. Sorry. Okay. Yeah, and the goal is actually, as I mentioned, is to track the progress of a necessarily robust model in a standardized way. And there are several parts in this benchmark. So first, we have a leaderboard or several leaderboards for several threat models, and containing the evaluations of the most effective defenses. And at the moment, we have a 150 plus entries, and this is kind of growing because we keep accepting new submissions. And then we have a model zoo, which contains actually the robust models. So okay, not all the models containing the leaderboard are in the model zoo, but I would say most of them. And okay, the goal is clearly to make easily available all the robust classifiers so that people can use them for their own research, and it makes much easier to actually evaluate further the robustness of these models and use them for other downstream tasks. Okay, and finally, thanks to our evaluations in the leaderboard and to the models in the model zoo, we can actually provide some analysis about various aspects of robust models beyond robustness itself. So, for example, we can just show some statistics about them, and then analyze other properties like calibration, fairness, privacy, and others. Okay, now we have a quick look at the various components of robust bench. First, in the leaderboard, which are the datasets and threat models we consider. So about datasets, we have the most common commonly used like computer vision datasets, at least image classification datasets, which are like cipher 10, cipher 100, and ImageNet. And as the threat models, we also consider them like the most popular ones, so which are L-infinity and L2 bounded adversarial perturbations, and common corruptions. Now, common corruptions are not adversarial attacks in strict sense, in the sense that they are not optimized to fool the network, but they are just like, as you can see in the figure, some corruptions of original images. So this is just a fixed dataset introduced by Hendricks et al. Some years ago. Okay, and here in the table, there is like an example, like a short summary of the entries in the model zoo and the leaderboard for each threat model and dataset. Okay, this is not up to date because it was taken from the paper, and in the meantime, we have added several models and entries. Okay, Then the main part about benchmark about robustness is the evaluation of robustness itself. And okay, as I said, for common corruption, this is quite straightforward since it's not an adversarial attack, but we just need to compute the average accuracy on a fixed test set. And this is basically for each image, 15 types of corruptions are applied, and each of them at 5 severity levels. So we have this big data set, and we just computed the average accuracy, classification accuracy, right, on each classifier on this fixed data set. And this is it. Okay, instead, for LP-bounded threat models, we use as a standardized evaluation auto attack, which we introduced some years ago. And this is an ensemble of white and black box attacks. In particular, we have like APGD, which is a variation of projected gradient descent, which is kind of the most popular method for white box attacks on different losses. And we combine it with a FAB attack, which is another method, another like white box attack, which like actually minimizes the size of the perturbations. So it's a bit of a different type of attack. And then we have a square attack, which is a black box one. And it's quite efficient, so we can actually run this evaluation quite fast. Okay, and this was shown to be quite like reliable across different data sets and threat models, and of course classifiers. Okay, this is the first like component of the evaluation. Then we have external and adaptive attacks. This means that every time we have there is a further evaluation available about a classifier, we just add this to the leaderboard. And there are a few cases where actually auto attack was combined with other methods to improve a bit the robustness evaluation. So yeah, we in the end want to track actually the most accurate evaluation which is available. So we are happy to integrate and to accept submission of new attacks. Okay, and finally, since as I mentioned, we cannot like foresee every possible case, and then there might be corner cases where like a standardized evaluation doesn't work. And we introduced a flag which suggests in which cases actually evaluation of auto attack might be unreliable. And so the flag is triggered by the fact that the black box square attack actually improves the robustness evaluation of the white box methods. And okay, this was also like formalized, let's say formalized in prior works. For example, a work about Carlin et al. 2019, I think, where in the case where black box attacks perform better than white box attacks, there might be some form of gradient obfuscation, and then further evaluation is necessary. So yeah, so we use this heuristic to flag which cases might require adaptive attacks. Okay, now about restrictions on the robust models we accept. Well, we have just three main rules, and okay, the first is that models should have in general non-zero gradient with respect to the input. So this is to rule out some like defense, like quantization of the input, which basically makes, since you don't get any gradient, standard methods do not work, but and they require some adaptive attacks, definitely. Or similarly, we require the models to have a deterministic forward pass. So we exclude basically randomized defenses. This is because these are a bit harder to evaluate, in the sense you should use, for example, something like expectation of a transformation, and there is no standard evaluation like protocol available. Okay, in general, for example, randomness, this is not so might work for robustness. For example, we have this case of randomized smoothing for certified robustness even. So we just cannot, we just exclude it from the leaderboard at the moment because we don't have a standardized way of evaluating it, evaluating the robustness. Okay, and finally, we take models which do not have optimization loops in the forward pass. For example, is test time defenses or GAN-based defenses where there are some iterative projection on the data manifold. And again, the reason is that evaluating these defenses is quite difficult, especially in an accurate way, in a standardized way. And but clearly, these are like restrictions which we have at the moment, and we would be happy to lift at least some of them as soon as a standardized evaluation method is available. Okay, now maybe a short look at the website. Right, this is an example of how the leaderboards look like, and which are the available ones. So we have the method. We have some notes about the method. We provide clearly standard accuracy, robustness given by auto-attack, robustness, best known robustness, which basically includes also adaptive external evaluation. So here, for example, it's like a 0.02% lower. And we have like the flag I mentioned earlier about potentially unreliable evaluations. Then we have whether extra data is used for training or not, since this has been shown to actually influence a lot the performance of the model, as well as the architecture. Then we show it, and finally when the paper appeared. Okay. Okay, this was about the leaderboard. Now we can talk a bit about the model zoo. Okay, as I said, the main goal of the model zoo is making the robust classifiers easily available, and then we provide like unified access to most of these other robust classifiers. We actually just a couple of lines of code so that downloading the checkpoints and restoring the models should be done automatically quite easily. And these models, like having access to robust models, can be used for new research, for example, meta-analysis or fine-tuning, or just as a source of a strong baseline for different tasks, actually. Okay, and together with this, we also provide a tool to benchmark new models. So we have, again, just with a couple of lines of code, we can run the evaluation, standardized evaluation for the different threat models on a new classifier, right? On your own classifier. Okay, finally, the last component of the Robust Bench project was about the analysis. Okay, we can even start with some just plotting some statistics about, in this case, the infinity robust models. And okay, for example, progress over time, we can see that like we have some increases, at least in the top performing models, over like in this case over conferences. Okay, and then we can plot like in the second plot there is they reported the robustness, robust accuracy in the original papers, and the robustness given by auto-attack. So in here we see that, okay, this is diagonal, so many points are like on the diagonal or below the diagonal, which means that in basically all cases auto-attack actually improves or actually matches the robustness reported. So it means that it's a quite reliable source for a standardized evaluation. And finally, some statistics about the models themselves. So the orange dots are the models with extra data, and the models without blue dots are the models without extra data. And okay, this is kind of known in literature, but we can confirm this with on many models that extra data actually improves both clean accuracy, so in the x-axis, and robust accuracy on the y-axis. Okay. Okay, second part. So this was just using basically the evaluation for the leaderboard, but we can also use the models, the model zoo to evaluate other aspects of robust models. For example, how robustness influences other metrics. And here there are just two examples. One is about calibration. So we computed expected the calibration error on robust models and on a standard model, which is here at 0% of robustness. And okay, this is done with the temperature rescaling. So basically already optimizing the calibration when computing it. And even with this temperature scaling, we see that actually the robust models are worse calibrated than the standard one. But the standard one is here at this 1%, and the others are like higher. Okay. And the second example is about privacy leakage. So it's this is on the x-axis again. There is the robust accuracy, and the y-axis is the like inference accuracy using confidence. So basically, one wants to know if a point was in the training set or not, and you can use confidence. Like the most simple, I guess, way to do it is through confidence. And in this case, basically here the standard model, and here the like the robust ones. And in this case, we cannot really say that robust models leak more or less training data compared to standard ones, since I mean the distribution is quite around the value of this standard model. Okay, these are just two examples, but on the paper we have also analysis about performance distribution shifts, auto distribution detection, fairness, smoothness, and transferability. Okay, this concludes kind of the first part about like the current status of the benchmark, right? But now that this is like this exists, we would like also to extend it if possible, right? And there are several like directions toward which we can expand it. And like the first one could be new threat models, like for example, sparse attacks, the serial corruptions, perceptual attacks, and so on. But also new datasets. A second direction, which is kind of very interesting, is adding like leaderboards for other types of defenses, for example, detection methods. And in this was work from like a recent work from iClear 2022. So yeah, I just accepted. I'm not involved in this at all. But so these guys tried to actually provide some standardized way to evaluate detection methods. And I can see that this could be like a first step toward us, like having a similar leaderboard for these detection methods. Okay. And the final point could be, as I mentioned earlier, right, it would be relaxing the restrictions on the allowed models when this is possible. Okay, and basically to extend a benchmark, we need, as I said, a standardized evaluation and a good amount of models, which means that the threat model is popular enough. So in the rest of the talk, I will focus a bit on the new threat models and datasets. Okay, the first thing is about extending it to a new threat model. And in this case, so the simplest one, I think, is the L1 threat model, since we already have L2 and L infinity. And like our first goal was to extend out attack to L1 bounded perturbations. Okay. So we start with the APGD, as I mentioned, is like one of the attacks in out attack, and is like a variation of PGD. Okay, PGD-based attacks actually, so how do they work? They want to solve this optimization problem to generate adversarial perturbations. And okay, the problem is just maximizing a function with in an L1 ball around an original point, a given like input point, and with this while staying in the image domain. In this case, we can rescale it to 0, 1 to the dimension. And the PGD is like a quite simple iterative scheme, which has like a gradient step. So you do just a gradient in some direction given by the gradient of the loss function. And then you project, if necessary, you project the point in the feasible set. So basically, in this case, is the union, so the intersection of the L1 ball, and the image domain. Okay. Okay, for infinity L2, PGD has a very like standard forms, and but for L1 there is no standard version, and the existing ones are less effective than other white box attacks. And like our approach to this is that for L1 actually we need to explicitly consider the role of the image domain 01 to the D, which actually this is not really done in, at least in L2 for the L2 threat model. And yeah, so the first thing, so we want to adapt to this PGD scheme to this intersection of L1 ball and the box 01 to the D, right? So the first thing is we want to have a projection onto this set, and because we know that actually the existing versions of PGD for L1 they don't use an exact projection, but they first project onto the L1 ball and then clip to 01. To 01, and this is just an approximated solution of this projection problem. So what we show is that actually this problem can be solved in d log d time, so complexity, and basically this is the same. D is the dimension of the space, obviously, and this is the same complexity as of the projection of only the L1 ball. And okay, and the second one is that the second insight into this problem is that the exact projection actually on the intersection allows to better explore the feasible set compared to the approximated one, which leads to stronger attacks. And okay, this can be seen like intuitively from the plots. Like on the left, there is just like an L1 ball, and in this in 3D, of course. And on the right, there is the intersection of this L1 ball with the 01 box. And we can see that these sets are quite different, so also projection is likely to be a bit different. Okay, so this was the projection step. The second part of the PGD scheme is the update step. And in PGD-based attacks, usually one adopts the steepest descent direction for the gradient step, right? And basically, steepest descent direction is just a solution of maximizing a linear function over our set, our feasible set. And okay, for the L1 ball alone, right? If we didn't have this box, this would be just taking a step in the component of the gradient of high with the largest magnitude in absolute value. But here we show that for the intersection of L1 ball and box, the sparsity of the steepest descent direction depends on the current point. So we cannot say in advance which is the sparsity of this update. Okay, and instead for the existing versions of PGD, use updates with either fixed sparsity or random sparsity, random in some range, but not depending on the point. So for L1 APGD, we actually adopt updates with this adaptive sparsity. So which means that we start with low sparsity, because so basically the updates are like have something around 20% of non-zero components. And this is effective because in this way we can like explore the input space quite efficiently. And then after m steps, we adjust the sparsity of the update. So we we force this sparsity, and depending on the sparsity of the best update found until this point. So basically, in this case, X max is the point realizing the highest loss until this point, right? And X is the original point. So basically, we take the sparsity, the zero norm is just a sparsity, and we reduce it a bit, and we use this as sparsity for the next step. Okay. Clearly now we have the sparsity of the gradient step. Now we need also step size, and this is also adaptive. And in particular, we change it according to how the sparsity of the updates changes. And the idea is that if the sparsity doesn't decrease, so basically it is this first case. We want to actually reduce the step size, right, for convergence, basically. But if actually we reduce significantly the sparsity, the idea is that we are exploring a different portion of the input space. So again, we want a larger step size. So basically, we reset this eta to the initial value, which is a larger one. This is how the step size is chosen, and finally, since the geometry of this intersection is quite complicated, we found that to better results, we can start actually from optimizing the loss in a larger ball. For example, so in particular, we start optimizing loss in a L1 ball with a radius 3 times epsilon. For 30% of the iterations, then we project onto the L1 ball and box with radius 2 epsilon, and optimize for the other 30% of iterations. And just for the last 30% of iterations, we actually optimize the loss in our really actual target L1 ball. And the idea why this is useful is because of geometry, but with starting from outside the final ball, we actually find better starting points for the final optimization. Okay, now some curves. And so first we compare our new scheme with this is L1 APGD, right, which combines all what I've said. And we compare to other versions of PGD-based attacks for L1. Okay, for the plots, we have, so in the top row, we have, on the x-axis, it's always iterations, so we take 100 iterations. And we plot, so in the first plot is the loss function, the loss achieved by the method. And so for the red curve is our L1 APGD in standard version with just a single epsilon value, and the blue curve is curves are the versions with multiple epsilons. So this is a thing of reduce starting from outside, as I mentioned. And of course, this starts just at the iteration 60 because we optimize in the final ball feasible set just for the last 40% of iterations. Okay, and so our curves go achieve quite a higher loss than existing methods in green and black, and the same is for the robust accuracy, which is in this case the lower is better, right? So it means that the attacks are strong. In particular, we also test for all the methods, so using the exact projection, which are the solid lines, and the approximated projection, which is just a projection on the L1 ball and then clipping. And we see that using the exact projection actually yields some improvement in basically all cases, and even for the other methods, right? Even if the here the improvements are smaller, right? One could see that even for existing methods, replacing the projection, approximated projection with the exact one actually improves the final results. Okay, and the second, the bottom row actually shows the adaptivity to the budget of our method. Basically, see that depending on the total budget our method is given. For example, we have like either 10, 25, 50, or 100 iterations. We basically there is like a simple adaptive schemes which actually adjusts the like the procedure to the total budget, right? So the curves are not overlapping, right? But depending on the total budget, they are steeper or less steep at the beginning, but achieving very good results, right? Or like even with just 25 steps, we are or 20 steps, we are similar to like previous methods. Okay. Yeah. Okay. Here I talked about APGD, right? But in AutoAttack there is also Square Attack, and which originally didn't have an L1 version, but we can actually reuse the projection onto the intersection of L1 ball and box in the original scheme, which is based on random search, and we can extend the like the Square Attack to L1. So this was just a small change, but actually gives a strong L1 attack, a black box attack. And okay, now we can compare like different methods. In this case, this is a comparison on Cypher 10 with epsilon, so the radius of the L1 ball 12. And we use just a single start, right? Basically, these all methods are run without restarts. And the models, several models, and basically these are all of them are actually robust. This with respect to some norm, right? Some are robust for L infinity, some are robust for L2, some are robust for multiple norms. And okay, these are existing methods, including Fab, and we see that our APGD, in this case on the cross entropy loss, improves, achieves the best, so the lowest robust accuracy, which is the best in this case. And on all cases except for one, where actually Square Attack, which is our like black box attack, achieves the best results, because in this case there is some kind of gradient obfuscation, which actually makes like quite a difficult optimization with the gradient-based methods. And like as a side product, we can also see that the Square Attack actually improves only this point-wise attack, which was like a previously proposed like black box attack for this threat model. Okay. Okay, now that we have these two new versions of APGD and Square Attack, we can extend AutoAttack to the L1 threat model, since Fab already had like natively an L1 version. And we can now test robustness with in some standardized way with no parameter tuning. And we can see like here is like a similar comparison, like the same models as before, with the difference that here like with a higher budget was given, and we see that AutoAttack achieves best results in most of the cases, and or is very close. And okay, this WC is actually the worst case, so we take the worst case over all the attacks which are not included in AutoAttack. So quite many attacks actually. And like we also tried, of course, like using L1 APGD for adversarial training, like with 10 steps. And actually, this score works quite well and gives quite a high robustness in this first model in L1. Okay. So first, so this was kind of a first possible extension of like a standardized benchmark to a new threat model, right? In this case, like L1 attacks. And yeah, there is no leaderboard at the moment, but yeah, hopefully there will be one in the future. Okay, maybe quickly I can go over like also another improvement if I have time. Okay, so it will be quite fast. Last part about how we can extend the benchmarks to a new dataset. Right, in this case, imagine it. So the problem for ImagineIt is not evaluation, right? Because we still have we can use the standard threat models, L2, L-infinity, L1, why not? And but the problem is actually to get robust models, right? Because as a cell training with in general with the large models and on very large data sets like ImagineIt and a high resolution with high resolution images, actually is might be very expensive, and it's not clear how feasible it is to do experiments with this, in the sense that you cannot test too many things because like training is super long and super slow. Okay, the idea, right, in this work was to actually use to not retrain models from scratch, but just use a quick fine-tuning of an existing robust model to change actually the kind of robustness. So basically, we started with a model robust with respect to LP, and then we fine-tune with adversarial training with respect to LQ. So with a different norm and or for multiple norm robustness, and actually we get a high robustness in the target threat model. So here in the picture, there is a summary of the results on Cypher 10 with only 3 epochs of fine-tuning. And this is basically, we started in the center. There are the statistics of the most robust at the time model in L-infinity, which doesn't use like extra data, so extra like a synthetic data. So this was state-of-the-art L-infinity robustness, this is 65.6. And we can see that, okay, it has quite a high L2 robustness too, but okay, very like lower than state-of-the-art, but almost no robustness in L1, and clearly the same in the union. So the union is the worst case over L-infinity and 2 and L1, right? So a point is robust in a union only if it is robust with respect to all the individual norms. Okay. Then we do 3 epochs of fine-tuning with respect to L1 with our L1 APGD, actually of this model, and we see that actually this is sufficient to get L1 robustness from 8.1 to 70.2% robust accuracy rate, like which is better than like what I showed earlier for the other models. And of course, we lose quite a lot in L-infinity, but okay, this is kind of expected. And we can do the same, but with our EAT. EAT is just like a method which also introduced in the same paper for multiple norms robustness, right? So the goal here is to optimize union. And we see that again with the 3 epochs, we can like raise this L1 without losing that much in L-infinity. And also in L2. Actually, L2 improves even a bit. And again, we can achieve like some state-of-the-art multiple norms robustness with this fine-tuning. And clearly, this is important because even on Cypher 10, because this is a super large model, right? Okay, at least for like the adversarial robustness world, and as wide as 7016, so it takes quite some time to train it. And we don't want to train like for like 200, 300 epochs just for L1. So since we have available this model, right, we can just fine tune it. Okay, and finally, this the main thing is extending this to ImagineIt, right, where there are not many robust models, and we show that basically with the same method we can but with just 1 epoch we can turn we can change actually the type of robustness of like already robust classifiers, right? And so here for individual norms, right? For example, if we start with RSNet robust for L-infinity, right, and we fine-tune to L2, we can greatly improve. The robustness for L2 goes from 17.7 to 41.5, and if you fine-tune from to L1, right, this starts from 0 and can go to 27.4, right, which is in just 1 epoch. Okay, and actually this works similarly for transformers, right? So we also tried with the same scheme. This works as good as for ResNets. And also there is an observation of like L1 especially improves a lot. And the same works also starting from an L2 model. In this case, we go from L2 to L infinity and L2 to L1. Okay, and finally, we can do the same as for several times for multiple norms. So here the target is the union, right? And again, we start from the resonance. With the resonance, we can start from 0 and go to 22.6, so over 22 for both resonance and resonant 50 and this small transformer. And same for L2 robust models. Okay, so this kind of concludes the talk, and like a couple of small thoughts about this. So we talked about like standardized benchmark, and doing this is actually possible, like for the cell robustness, if we like set some conditions right on the loud model, and in this way we can actually track the progress and actually provide some useful tools, I hope, like with the model zoo and the benchmark tools. And then like currently we have these restrictions, right? And in general we are like we kind of limit a bit the scope of the benchmark, right? But we should aim at lifting these restrictions and making everything more inclusive. And yeah, finally we want to, as I said, we want to extend to other threat models and datasets, and clearly this has to follow kind of the interests of the community. Yeah, thanks a lot. Thanks a lot for the attention, and I will be happy to answer questions.
Thank you very much. There are several questions coming in the chat box. Yeah. Can you?
So okay, yeah. Can I just go through it?
Sure.
Okay, so okay, I guess the first was about example of overestimation, example of the actual robustness, right? So I don't have like so there have been several examples, right? So overestimation can be given by different for different reasons, right? Especially so the attack is not, basically the problem is that usually the attack is not strong enough or is not suitable for the given defense. And so some cases are basically some here, right? So for example, this was so on the x-axis were porty robustness, right? And on the y-axis that with auto attack, right? So and here therefore this basically these points below the diagonal, the drop is quite significant. So I don't know if this answers the question, but okay, there are several papers like showing this. For example, there is a literature about from like Nicolas Carlini. There's this paper from Atali et al. In 2018, ICML, which like can give a much more detailed overview of this case. Yeah, about privacy leakage, yes. So okay, so the metric. So here should be just like here is basically the percentage of training data which is identified right through the confidence. So if I'm not wrong, so I didn't do this myself, but if I'm not wrong, so you just compute the confidence, the average confidence of, so you take a point, you compute the confidence, and according to some threshold, you decide if this belongs to a training set or to a test set. And okay, the assumption is training points have higher confidence because they were used during training, right? But this is okay. This is unclear, right, in general. And this seems so for standard model. Basically, I guess this accuracy is around this 58%, and for robust models, this is like it varies quite significantly, right? So it's not, and I don't see any correlation between the robustness itself and privacy leakage. Okay, I hope this answers the question. What happened behind is fine-tuning to enhance the union over the robustness. Yes, so okay, we can also go there. For the union, yeah, so you mean when we optimize, basically in this case, when we optimize for the union itself. Okay, so we optimize. So okay, the idea behind this IET is that we can optimize just. So what we do, we optimize just L infinity and L2, L1, right? We do adversarial training for L1 and L infinity, but we alternate them, right? So for each batch, we basically sample one of the two norms with some scheme, and we optimize it with adversarial training. And the idea behind it is that there are some geometrical arguments. Is that the extreme norms in some sense contain also the like the intermediate ones. This is just a high-level idea, and so basically this is sufficient to actually preserve robustness with the for the intermediate norms, and or create if there is not. And so this gives provides also some like a good robustness in the union. So that's so. But here the goal is indeed to optimize the union. Okay. Yeah, also about L1. So there was a question about. So if there's a further question about the fine tuning, I can also give some more arguments. So okay, about adding L1, L2 to ImagineNet to the benchmark. Yes. So this is kind of personally, yes, I would like to. I think the main thing, as I mentioned at some point, is that we need some critical mass of models, in the sense that it must be something which is kind of seen as useful, right, by the community. And so like I hope there will be more models robust in more different threat models. But yeah, I would be really happy to add both L2 and L1 to robust bench. Yeah. Okay. I guess I've gone through all the questions. So thanks a lot. Yeah, I'm glad to hear that. Like our work has been useful, right, to other people.
Indeed. All right. Since no further question coming up, let's thanks a lot to Francesco to give us his wonderful talk. His research attacks is indeed very helpful to our community. Thank you very much. In the future,
thanks again for the
yeah.
Thanks again.
Yeah, we sincerely welcome you to visit us in Tokyo in our Nihonbashi office. It's in the center of the Tokyo. If you drop in Japan, in Tokyo, we sincerely welcome you to come visit us. Thank you very much. Yeah. All right. This is the end of today's seminar. Again, we thanks a lot for our valuable guest. Thank you. Bye-bye.